So let's go ahead and get started. All right, we're going to return to electron counting in oxidation state land today. Last time we did a handful of examples. We talked about counting them all together versus counting each metal separately. And the tricky thing there when you have a metal-metal bond is that the metals raise each other's valence electron counts. So, if you have a metal donating one electron to a neighboring metal, the metal that's receiving that electron, its electron count goes up. But the metal that's donating the electron also uses it for its electron count, and it takes one from the metal it's sharing with. So when you make a metal-metal bond, there are two electrons that are raises the total count by 2. And so you have to count accordingly. Bridging carbonyls. Carbonyls have 2 electrons to give, and they share them equally between the metals. If you got 3 metals around a carbonyl, then 2 electrons shared with each of the 3 metals. We talked about bridging ligands like halide and phosphide, one giving X and one interaction being X and the other being L. Of course, the interactions are the same, but the total number of electrons being contributed is 1 plus 2 for X plus L. So bridging ligand can give 3, depending on how many bridges it makes. Hydride ligands, we think about the BH bond in diborane as donating 2 electrons to the other boron. So the bond pair makes a L-type interaction with a neighboring metal. We showed one example of a bridging hydride ligand in a metal-metal bond, and it's tricky because metal-metal bonds and bridging hydrides sometimes lead to a confusing situation. So people draw the metal-metal bond, but there isn't always necessarily a metal-metal interaction there. Generally, when assigning whether or not there's a metal-metal bond, you ask, can I raise the electron count to 18 electrons this way? Metal's trying to get to a full valence shell, so it will take electrons to get to that 18 electron count. So you can decide how many metal-metal bonds are there by measuring that number. It's tricky, however, because sometimes the symmetry is not there. So the real situation is more complicated than just the stick drawings. But when making a guess as to what the valence of the metals are and whether there are metal-metal bonds there, the easiest thing to do is to see whether there are 18 electrons. Okay. So we're going to keep doing that today. Oh, we also talked about some examples where you can make your life easier by pulling off charged fragments, right? We're trying to get you to use the neutral ligand formalism or the neutral fragment formalism, where you pull off a neutral thing and you ask how many electrons it donates and use that in your count. But you can also pull off charged things and still count electrons. The example that we gave was the cobalt cyanide compound, where you pull off a cyanide anion. That's 2 electron fragment that's negatively charged. That sort of helps to count the metal center. And we'll do some more of that today to kind of make that clear. All right, so we did Wilkinson's catalyst. Let's do, we introduced formal oxidation state. We did the nickel diallel too, didn't we? We do nickel dial, and did we do CP molybdenum tricarbonyl hydride? No. Okay, so let's do that one. All right, so let's do some valence electron counting first. How many electrons for CP? 5. We've got 3 CO ligands. 2 electrons each gives 6. What is the neutral fragment for a hydride? It's an H atom. 1 electron. That's an X-type ligand. We have the molybdenum. What's molybdenum's electron count? Chromium, molybdenum, tungsten are in the same column. That's 6. Chromium, molybdenum, tungsten are 6. So we are 12 and 12 and 6 is 18 electrons. Now, what's the oxidation state? How do we determine oxidation state?
Charge.
We pull off closed shell fragments.
So the CP is neutral. The hydride will have a negative charge on it. And then those COs are all neutral because you have a plus and a negative. Negative on the carbon and positive on the.
Okay, so what is the oxidation state?
Molybdenum 1, and it's going to be D5.
Okay. People like that? Yeah? Anybody have another? Cheyenne looks upset. What do you think, Cheyenne? Do you have another idea? Okay. 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 So you like molybdenum 2 starts with 6 electrons, right? So that would be D4. So Cheyenne likes molybdenum 2, D4. Anybody else? Any other ideas? All right, how many people like molybdenum 1? How many people like molybdenum 2? Anybody who didn't raise their hand have another idea or just lost? Anybody want to say anything about this problem? Ask a question, maybe? Nothing? We need to do some push-ups to get started this morning. CP, what type of a ligand would you call this? Is it X, L, LX, X3? Say that again? L2X, right? Let's draw the closed or the neutral ligand fragment for a second. Okay. There's your 5 electrons. We said CP is 5, right? Let's draw the closed shell fragment for a second. Oh, looks like a weird smiley face. We have 2, 4, 6 aromatic anion, right? So this is a -1. You could buy sodium cyclopentadienide from Sigma Aldrich. It's a classic anion. So there's an anion. Hydride, going to be an anion. If you pull it off as a closed shell fragment, or an H atom if you're pulling it off as a neutral fragment. And the COs are just neutral fragments, closed shell. They're hypovalent, so it's a little bit confusing, right? But you borrow some electrons from the neighboring oxygen to close the shell for the carbon and develop the 2 charges. These are L-type ligands. Okay, so only these guys raise the oxidation state. This is molybdenum 2, E4. Okay. All right, so that's how you figure it out. You got to pull these things off and count their electrons and then ask, when I make a connection to the metal, am I going to take one of the metal's electrons? The answer is yes, because this guy only has 1, right? So you got to take one from the metal to make a covalent bond there, and it's like metal plus ligand minus. There's your ligand minus form. where it's taking an electron from the metal. When you bring up a CO ligand, it brings up 2 electrons to the metal. It doesn't take any electrons from the metal to make that bond. When you bring up a hydrogen atom, it takes 1 electron from the metal to make that bond. Okay, so the ligands that take an electron raise the oxidation state, and that's why it's molybdenum 2. Go ahead.
So basically for every X type of ligand, it's gonna, so basically if you have 3 X type ligands, then it would be a little bit.
Correct. Unless there's a charge.
Right.
Yeah, so you have to think about the charge also. You know, if I had this compound and it was a cation, then what would the oxidation state be? Let me just say it to you this way. We got molybdenum 2. I'm going to do some electrochemistry on it. I'm going to oxidize it by 1 to get to molybdenum 3. Then it's a cation. Or I could reduce it by 1 electron and make molybdenum 1. Is that experiment going to work? It has 18. So if you put an electron on this thing, it's probably going to fall apart. And the electron isn't going to go on the metal. It's probably going to go on a CO. Perhaps. And the ligand would probably fall off or something like that. Yeah?
So if a fragment, or sorry, closed shell fragment, when we pull it off of the molecule, because it's a L2X1, is that going to, can you determine if a fragment will be charged when trying to find the oxidation state by doing that? By going, well, how many X type ligands do I have? How many X type interactions and L type interactions?
Yep.
So if I have an X type interaction, that means I'm going to have a single negative charge when I pull it off.
Yes. All right, let's do one of my favorites. We're going to talk about carbene ligands. The carbene. Well, there's 2 types of carbene ligands. Carbene is kind of a misnomer, really, but what's a carbene without the metal around? Anybody know? Divalent carbon. The classic is methylene. There's a very hot debate as to whether methylene was a singlet or a triplet. Organic chemistry caused a lot of angst. We'll call them just Schrock type. That's fine. All right, so there's 2 types of carbenes. One named after Dick Schrock, very powerful chemist, excellent scientist, Nobel Prize winner, largely because of his interest in metal carbon multiple bonds. This is a classic example of a Schrock type carbene. This cyclopentadienyl tantalum methylmethylidine. That's a methylidine. All right, so let's count this thing in terms of our neutral ligand formalism. Okay, so CP, there's 2 of them, 5 electrons each. We've got a tantalum. How many electrons on tantalum? Vanadium, niobium, tantalum. Have 5. We've got a methyl. How many electrons for methyl? 1. That's just a simple X-type ligand, right? How about this CH2? Why 2? I mean, you pull it off as a neutral fragment, right? So you got to cleave 2 bonds here. Carbon has 4 electrons. Those 2 hydrogens are sharing with 2 of them. So there are 2 electrons remaining. That's why you get a double bond. Each electron pairs with the tantalum center. So this is 2. That is 18. Closed shell tantalum.
So would you consider the CH2 to be like an X2 or just an L?
Great question. In a shock type carbene, a CH2 is best thought of as an X2 ligand. Okay. So let's dissociate this stuff as closed shell fragments for a second, okay, instead of our neutral ones. We did neutral fragments over here. Now we're going to do closed shell fragments. CP is an anion, right? Already talked about that. Methyl comes off with 2 electrons on it instead of just 1 this time, right? So that's methide anion. 2 electrons in each of those bond pairs. That's 6 electrons in bond pairs, and a lone pair gives you 8 electrons around carbon. Okay, that's why this is closed shell. This one here, what's its charge? It's 2 negative, 2 minus, right? We're trying to get 8 electrons around the carbon. There's 2 hydrogens stuck. Those CH bonds have 2 electrons each, so that's 4 electrons. We need 4 more electrons around the carbon. You get that by having 2 lone pairs, right? This guy's got a lone pair. And that CH2 is 2 minus with 2 lone pairs. So what does tantalum have for charge? Two, 3, 4, 5, right? 2 CP. So we got tantalum 5. How many electrons in tantalum 5? 0. And all is right with the world. You're on the left-hand side of the periodic table there. That's an electropositive metal. Okay. Tantalum 5 is a good oxidation state. You see tantalum 3 compounds too, sometimes. Tantalum 5 is good. All right. So this type of carbene is really well described by that picture. Okay. It's an electropositive metal. The carbon, the methylidine, the CPs, they're sort of like anions around an electropositive metal. This thing is nucleophilic. You can think about it as kind of having a negative charge out here and a positive charge over here. That's a good description for a molecule like this. Okay? It's like a Grignard reagent or something like that. Tantalum is an electropositive metal like magnesium is. All right, let's do the other type. Fischer type. I maybe don't have enough room for this, do I? I'm going to do a new board. Sorry, I didn't need to cram that in down there. Fischer type. So the classic example is this one here. Pentacarbonyl, tungsten, carbene with a methoxy group. And this one is different Because you can also write this structure. That's another resonance structure, right? Because you got some lone pairs out here. You can push those lone pairs down toward this carbon, and you can push this bond pair onto the tungsten. And when you do that, the tungsten develops a negative charge, and the oxygen develops a positive charge. Very different than an alkylity. I would call that an electron-rich pi system between the oxygen and the tungsten and that carbon. And so, yeah, that is not the usual way that people talk. That name means something specific. But yeah, you could think about this as pi donation. So, different way to ask that question is which one of those, or to state that is which one of those drawings makes more sense, which is a better descriptor for this compound. Okay. Before we do that, let's count a little electron. Let's do the valence count and all that stuff. All right, so we have 5 COs, 2 electrons each, tungsten 6, and then we've got the carbene. How do we count that carbene? Two X-type interactions, just like you see over here. Okay, so we'll give it 2. And that's 18 electrons. Now, let's do the closed shell fragment. Right, that's the closed shell carbene fragment. It's a 2-. So you've got 1 ligand here that raises the oxidation state by 2. Right? How many electrons on tungsten? 2. How many d electrons on the tungsten? 4. That's d4. Okay. Now, let's do the other one. We got 5 COs. That's 10 electrons. You got a tungsten. That's 6 electrons. What else do we have?
Single bond coming from the Fisher, the new Fisher, the resonating Fisher carbene. But don't we also have the negative, an extra electron that's sitting on the tungsten now, so it's actually 7?
Yeah. Yeah, you got a negative charge on the metal. Okay, so this minus is going to give you 1 electron. How do you count this thing? Looks like an X type, doesn't it? I'm going to call that carbonyl. 1 electron, and that gets you to 18 electrons. So it's like the electron that was in this double bond over here from the carbon just got transferred to the tungsten. So you're counting it over on that side as a minus charge. And over here, it's part of one of the bond pairs. Okay, same number of electrons. What's the oxidation state over on the right? Is it tungsten 2d4? Tricky one. Let's pull off a closed shell fragment. Okay. That's a closed shell carbon there, right? It's kind of like the closed shell carbon on carbon monoxide in a way. Right? Neutral carbon monoxide is a plus charge on oxygen and a minus charge on carbon. It's very much like that. You can think about this thing coming in with its lone pair and just binding in an L-type fashion to the metal. And then you end up with this charge arrangement in the process of doing that. When we have carbon monoxide ligands, we don't write out these charges. But the way that we just counted this thing is very different than we do a carbon monoxide, right? Carbon monoxide, we draw a single bond to carbon, and carbon's got 4 bonds around it. So you could call it an X-type ligand, but then you have to do the formal charges, 1 on oxygen and 1 on the metal. We don't usually do it that way. We just say, neutral 2 electron donor, right? Same story, just a different fragment. So what's the oxidation state? Is it tungsten 2D4? Tungsten 0D6. The carbene is a neutral thing. In principle, you could put that in a bottle. A lot of people have tried, including me. Those are neutral fragments like carbon monoxide. It's not going to be a gas, but it's a. So you take tungsten pentacarbonyl. What's the oxidation state of that? Definitely tungsten 0. And you're adding another neutral fragment to it. Doesn't raise the oxidation state. Okay, doesn't change the oxidation state. This is tungsten 0D4. Thank you. B6, which is a very different situation than what we just said over here. So which is it? What's the answer? What's that? A mixture of both is a very good response. What's the real oxidation state? I mean, this is part of the problem with oxidation state formalism, okay? Is that there's this like this game of pretend people play where they try and tell you what the charge on the metal is. But the real charge on the metal is complicated. It has to be measured with some kind of spectroscopy. All ligands in metals have different electronegativities. There's different degrees of charge transfer, okay? So this oxidation state thing is not a real measure of charge. It's more of a statement of the valence of the metal ion, how many d electrons there are. That's useful for determining things like magnetism. Okay. Which is a better description, however, between these two resonance depictions? That's a fair question to ask. Do you think that a negative charge on the tungsten center makes sense? A positive charge out here on oxygen? Or do you prefer something that looks like this, where the charge is more out there on the oxygen and less on the tungsten? People like this one? I like this one. Why do I like this one? What's the justification for that?
I don't know, just because the metal having a negative charge on it, it's implying that you have more of a conduit. It's showing delocalization, I guess, because there's charges placed on the atoms, whereas the other one, like, I know that there's delocalization because of resonance, but it's like neutral, So the one on the right is going to show that there's a lot of electron delocalization happening between the metal and your ligand.
Yeah, so I mean, there is delocalization going on. The question is, where are the charges localized? If it was fully delocalized, you might say it's 50-50 of these two, okay? Why is this one a good description of where the charges are, is the question. Why would you ever want to write a minus charge on tungsten? Well, there are two reasons. One is that carbon likes to make multiple bonds with other small elements that can make short bond lengths. Pi bonds don't work very well in long bond lengths. So yeah, there's a double bond there. There's definitely a double bond there, but that bond is so long, it's not a very good double bond. That one's not so bad because oxygen is small, okay? So you get good overlap between those kinds of elements, and the overlap between transition metal and carbon isn't as great. That's one reason. The other is that this tungsten is surrounded by 5 carbon monoxide ligands. And carbon monoxide is a pi acceptor, right? These are hypovalent carbons accepting electron density from the tungsten center via pi bonds. There's 5 of them. So that negative charge can delocalize out into the carbonyls. Okay. So this is a pretty good description here. I should have said this description is like an L-type ligand. This description over here is like X2. Okay, that's a pretty good one. If this is the case, right? Let's say this is the dominant description. How do you imagine a fragment like that or a complex like that reacts? If you were to predict its reactivity, what kind of reactions do you think that this thing does? With the knowledge that this is a good description. You like it as a nucleophile? Where is it nucleophilic? The tungsten is nucleophilic because it's anionic. Okay, how about this fragment here? It's what? Well, what I see is a carbon-oxygen double bond with a cationic oxygen. How about a protonated ketone or aldehyde? If you protonate the oxygen of an aldehyde, would you describe that thing as a nucleophile or an electrophile? It's electrophilic, right? Another way to say this is that there's some carbocation character here that's being stabilized by that oxygen and stabilized by the electrons on the tungsten. The lone pair on the carbon is a nucleophile. The empty orbital on the carbon monoxide is an electrophile. So what is the dominant mode of reactivity? It does both kinds of reactions. It is much more electrophilic than that one down there. Okay, that one down there is definitely a nucleophile. It reacts vigorously with oxygen. This compound probably reacts with water and less so with oxygen, if at all. Okay, it's mostly an electrophile. This is the most rapid site of reaction. The bond pair is really tied up. It's a little harder to access. This is easier to access and generally reactive as an electrophile first, but it does both kinds of reactions.
So it will make the, it will just make an OH and will stay on to the tungsten.
Then it could also kick out the tungsten and you'd end up with a methyl ester and 2 hydrogens or something like that. Okay, so 2 different kinds of carbenes. When the metals are a little more electrophilic, you find these kinds of resonance structures, particularly when you have donor atoms out here. Okay, when the metals are electropositive and you don't have donor atoms surrounding the carbon, you get these Schrock type carbenes. All right, so notice how the oxidation state depends upon the resonance structure, but the valence electron count does not. That's a big thing. You want to get the if you want to get the oxidation state right, you have to know the resonance structure. Or I should say, you have to consider the resonance structure. This is one of the reasons why the closed shell fragment method is a pain in the butt. Because sometimes ligands have multiple different resonance forms, and you have to assign them one to do the electron counting. All right, let's do some complexes with metal-metal bonds. Metal-metal bonds are not polar if they're the same metal, okay? So in oxidation state land, you cannot conclude that the ligand raises or lowers the oxidation state because the electronegativities of the partners are identical, okay? So metal-metal bonds do not change the oxidation state. So for example, this pentacarbonyl manganese dimer is manganese 0, E7. 5 COs, right? Manganese, that's 10 electrons, manganese is 7, and then you have this manganese center bonded to it. That brings 1 electron, 18 electrons around those manganese centers, but you don't get a change in the oxidation state because the manganese are the same. Another one is rhodium 4 dodecacarbonyl. Cool little cluster. This is rhodium 0. Said to be rhodium 0 D9. Okay. But how about the valence? What are the valence of rhodium? How many electrons are the rhodiums using in making bonds? How many bonds do they make? Well, the L-type ligands are not changing the valence of the rhodium center because the rhodium is not the one donating the electrons, the ligands are. Okay, so the rhodiums donate 1 electron to making a bond to the other rhodiums, which makes them trivalent. Okay. All right, let's do another ambiguous case. This is a favorite of mine. We have a C6H6 up here and a C7H7 down there. And this whole thing is a cation. How do we count this thing? Benzene is what kind of a ligand? L3, 3 double bonds. Each one donates 2 electrons for a total of 6 or 1 per carbon. Okay, how do we do this thing? How many electrons for this thing? C7H7 with the ring in it. Loosey-goosey 7-membered ring here, but probably it's 7, right? 1 per carbon. Delocalized aromatic thing. But let's stop and think for a second here. There's actually a couple of different ways you can write out this 7-membered ring. So you might be thinking, well, you know, it's like a cyclopentadienide. So I'm gonna give it a minus, a plus and a plus, or a bond, double bond and a double bond. So that would be C7H7 minus. That feels familiar, you know, because 1x type and 3L types. In this resonance form, what is the oxidation state on tungsten? It would be +2 because you have one negative charge here that raises the tungsten by 1. And this complex is a cation, so we also raise the tungsten by 1. So this would then be tungsten 2, D4. But you also know, perhaps, this thing. What is that thing? That's aromatic, right? 4n + 2 electrons. You got 6 electrons in a ring. This cation has a special name. Does anybody know what it is? Tropylium. Tropylium. I don't know if you could probably put tropylium in a bottle. I'm not entirely sure. When you're doing mass spectrometry and you have a benzyl substituent, it'll fall off to make a cationic benzyl that rearranges into one of these. You see tropylium ion as a fragment in the mass spectra of a lot of compounds. C7H7 cation. What's the oxidation state on tungsten if that's the description of the ligand? Tungsten 0. Now this, you could say, well, it's aromatic, it's closed shell, you know, so cationic closed shell looks pretty good. One thing you can do, as I've been telling you, is to dissociate a charged fragment and look at what's left over. So let's pull off tropylium cation from this thing. What do you have left? Tungsten stuck to benzene. What's the oxidation state of tungsten stuck to benzene? 0, right? Let's do that again. When you see a compound like this with a charge and you look at your ligands and you say, well, I can pull off a ligand that has that charge. Let's do that. Tropylium cation is gone now. Now you have tungsten stuck to benzene. That's definitely tungsten 0. So you can bind tropylium cation to tungsten 0 like this and not change the oxidation state, assuming there's no charge transfer. Okay. So the question is, where are the electrons in the oxidation state formalism? The oxidation state wants to know who's most electronegative, right? Is it the tropylium cation or is it the tungsten center? Anybody have a feeling about that? Turns out tropylium cation is a pretty good oxidant. It's a carbocation, sort of, delocalized one. Tropylium is a pretty good oxidant. Would you say tungsten 0 is a good reducing agent? Well, if you ever broken a light bulb with a tungsten filament in it, you whippersnappers probably don't even know they used to make light bulbs with tungsten filaments in them. It catches on fire. Blue flash of light. Tungsten is pretty electropositive. Likes to make an oxide that's quite poisonous. So tungsten 0, you know, there's a lot of electropositivity here. Does it make sense to have a cationic fragment on tungsten 0? Yeah, not really. So where's the charge? Metal plus ligand minus, okay? This thing here, if you draw out its MO fragment, which we're going to do in a second, looks a little bit funky. Let's draw another one. Here's another one. C7H7 3 minus. Wow. Kind of freaky. Anybody like this one? Hey, it's aromatic, but it's weird. It's a pretty good description in this case, turns out. What's the oxidation state on tungsten? That's an aromatic closed shell trianion. This could be a trianion then. If I pulled off a trianion, what would this be? If we're going to get to a cationic thing overall, and this is a trianion, this is neutral, we can kind of forget about it, then you better have tungsten 4 plus, right? Trianion 3 minus plus a 4 plus gives you a 1 plus overall, okay? So this is tungsten 4, E2. Okay. Now, that is a pretty good description, it turns out. And the reason is that tungsten is electropositive. So if we have a C7H7 minus fragment, let's do the MO diagram for the aromatic system, or for this ring of p orbitals. Okay, there's the frost circle method. You guys know the frost circle? You take the 7-membered ring, put the point down, and you get a line at each of the carbons. Like this. That's the MO diagram for the pi system. How many electrons are in this pi system? Two, four, six, 8. Who do we appreciate? Okay. That's open shell. The C7H7 minus has 2 unpaired spins. And it kind of looks weird. Let's do C7H7 plus. Six electrons, aromatic. Closed shell, 4n plus 2. So this is a closed shell. Right? This one is also nice looking, but you've got an electropositive metal there. So if you look at the energy of the electrons on the tungsten, and you look at the energy of the orbitals on the tropylium fragment, you're going to find the electrons are above and will therefore transfer into that fragment. That's a way to think about it. Okay. This is a nice description for that reason. All right. So ligands can be described in multiple ways, depending upon the metal and depending upon the ligand. And you have to think about that when trying to count electrons. people get excited about these problems in lectures, you know, oh, which one is it? What's the best way to describe it? You have to have an intuition about how electropositive things are, and you have to be able to read into the possible resonance structures. You don't see that when you just draw a ring with a circle, right? But you need to be thinking that. Because if you say, hey, obviously that's tungsten too, somebody will say, yeah, think again. All right, so we're going to talk carbonyls a little bit more carefully. Oh, man. So we're going to do some carbonyl chemistry here. We're going to start by doing the MO diagram. For CO, okay? So we've got a carbon, got 4 electrons. We've got an oxygen, it's got 6 electrons. And those provide 2 p orbitals and a 2s orbital. And oxygen's got the same, but it's more electronegative. Higher effective nuclear charge. So they're a little bit lower. And what you're going to find is that you get a bonding combination down here. There's a bonding combination for those guys. And then you're going to get 1 sigma bond for these 2p levels. And then you're going to get a pair of pi bonds. Okay. So 2 of the p orbitals on the carbons and the oxygens point directly at each other and make a sigma bond. And the s orbitals also can make sigma bonds with each other. So you actually have 4 orbitals of sigma symmetry. And then there are 2 p orbitals on the oxygen and the carbon of pi symmetry. Okay. So you're going to get a pi bonding interaction and you're going to get a pi star. These guys are sigma. These guys are sigma star. Did I do that well? I'm going to adjust this slightly. I'm sorry. Change it up on you like that, but I'm just going to move it up a little bit. So let's put some electrons. We had 4 per carbon, 4 on the carbon, 6 on the oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. How would you describe that pair of electrons? If you had to assign it a name, that would be a descriptive name somebody would recognize about that compound. Which electron pair is that? HOMO is a good one, but I want something that's more descriptive about where it's located. Lone pair on what?
It's going to be on the carbon because the parent is close.
Okay. Let me ask you a different question. Forget about the MO diagram for a second. If I handed you a carbon monoxide and I said, what is the highest energy electron pair on this molecule? What would you say? Well, it's the carbon lone pair, okay? And it sort of makes sense that it's that way, partly because carbon is the thing that sticks to the metal, right? Carbon monoxide binds with its electron pair in this donating fashion. Carbon is more electropositive than oxygen. So it's better at giving up electrons than oxygen is. So the highest energy electron pair is probably on the carbon, not on the oxygen. All right. It's actually part of a sigma orbital that's delocalized, sort of. This is a carbon lone pair. Okay. What's this one? And what's this one? What's this one? What? It's a sigma bond, kind of, yeah. What kind of character would you say it is? Well, both of these are sigma, okay? I think of this as oxygen lone pair. And I think about this as the CO sigma bond. Now, why do I say that? Because this is closest in parentage to that. It's the deepest lying thing. And I would guess that the oxygen lone pair is the deepest lying thing. And that the sigma bond is slightly higher than that. That's sort of a way to talk about it. This one is definitely carbon lone pair in nature. And it is slightly antibonding. Okay, it's slightly antibonding. All right. So the HOMO of CO looks like that. And the LUMO of CO like that. Okay, there's your pi star. That's your LUMO. It's sort of carbon centered, right? Because the closest orbital parentage is the carbon p orbital. So it's sort of carbon centered. The pi star is weighted toward the carbon. The pi bonding orbital is weighted toward the oxygen. That's one of the ways that you can talk about carbon monoxide being a pi acceptor, not a pi donor. Because the pi donating piece is toward the oxygen, not toward the metal. And the empty piece is toward the metal. Right? That's why it's a pi acceptor. All right. So both of those interactions lead to COs bonding with metals. Let's take a look at a few compounds to see how that's true. Sorry. This CP star, zirconium dicarbonyl. This compound has a bond association energy. This is the metal CO bond association energy of about 40 kcals per mole. Okay. Turns out it's pretty hard to measure these things. Here's another good one, nickel tetracarbonyl, famously poisonous gas. Its density is pretty darn high. There are some gaseous transition metal compounds that have densities of like 12. Pretty cool. You fill a balloon with one of those things and you throw it and it flops on the ground, you know, instead of 10 times heavier than water. Whoa, it's kind of weird. Nickel tetracarbonyl. The CO bond association energy is 25 kcals per mole. Iron pentacarbonyl back up to 40. Tungsten hexacarbonyl 46. So what's the trend here? The weakest nickel, weaker than iron, right? Why is that? Well, what's the difference between iron and nickel? Iron is more electropositive than nickel. So that means what is making the CO stick? It's iron's electropositivity, perhaps. So then what is the dominant feature of the dissociation, or what's making the COs bind? It's that pi back bonding. Okay, that's one way to think about it. Zirconium, what's the oxidation state here?
CP star. Okay, so CP star has the 2 pi bonds, so it's 2x. But I don't think it has an L ring because it has the metals. Like these are not using it has the metals.
The metals don't do anything to its L or X assignment because they don't conjugate with the metal in any way, and the hydrogens in regular CP are the same. So it's isoelectronic with CP, sort of, from the perspective of the metal. So it's zirconium-2 because carbon monoxide is a neutral fragment in its closed shell form. CP is an anionic fragment in its closed shell form. So zirconium-2, all the way on the left-hand side of the transition metal series, those metals like to be in their highest oxidation states. 2 electrons, really good pi donor. Lots of charge transfer over the COs, and they have a high bond association energy. Tungsten hexacarbonyl is higher than iron pentacarbonyl, more electropositive, more CO ligands, but it's also a 5D metal. Okay. How big are these numbers? Like, what's a good bond strength? What's a CH bond strength? A 100. There's a range of CH bond strengths, okay? It depends which CH bond we're talking about, but about 100. That's a good reference point. Water's 120. CH bonds are about 100 kcals per mole. So is that a big number? CH bonds break, right? You can break a CH bond. This is 4 times weaker. Rates of reactions go, you get a factor of 10 every 1.37 kcals per mole. So you're talking about much weaker, okay, in terms of chemical reactivity. These are weak bonds. Bonds of about 30 kcals per mole fall apart at room temperature at a reasonable pace. So this stuff plates your lungs in nickel metal. That's why it's poisonous. Okay, it's falling apart. Well, of course, nickel plated lung sounds pretty bad. But yeah, CO is poisonous too. Yeah. All right. So 30 kcals per mole, you're starting to see some things happen at room temperature. So this compound's barely stable. It's a way to think about it. You can put it in a bottle. But generally, you keep it cold. All right, so let's do some resonance structures for CO ligands for a second, because that will prepare you for everybody's least favorite resonance problem that we're going to do soon. So we're going to do some resonance structures here. And in these structures, I'm going to draw out the formal charges. We normally don't, but I'm going to draw them in these cases. And you should too. Okay. So this would be a complete resonance structure, including formal charges. And this is the sigma only binding mode. And it turns out that, of course, you know, you can make pi bonds. So one of the things you can do is to push electrons onto the carbon and then push electrons out toward the oxygens. And when you take this electron pair and make it into a bond pair, you lose that negative charge. And when you push one of those bond pairs out onto that oxygen, you lose that positive charge. Okay. So this is the sigma plus pi picture. But you know that there are two bond pairs, two pi bond pairs that you can move. X and Y are indistinguishable. So this is another valid resonance depiction. Sigma plus 2 pi. Okay. Now, depending upon the compound, you can have any one of these situations or somewhere in between. And one of the things that changes when you do that are the bond lengths. Okay. So free CO is 1.128 angstroms. The carbon oxygen bond length. Metal carbonyls, the approximate distance of the CO bond is going to be 1.15 angstroms. That's typical. Okay. And things like formaldehyde have RCO bond lengths of 1.20 angstroms. Okay, so your average carbon monoxide complex has a CO bond length that's in between a double bond and a single bond from the bond length perspective. Okay, so the change in the bond length you see for that thing is sort of related to the bond order and bond strength. It also changes things like the vibrational frequency, as we'll see. As the bond length changes from double or from triple to double to single, what do you think happens to its vibrations? Now, how do we analyze this problem? The vibrational frequency is determined by the reduced mass, so how heavy the things are. Heavy things vibrate more slowly. Little things vibrate quickly. But what's the other thing that determines that frequency? The force constant. How tight is the spring? Is it a loose spring or is it a tight spring? And would you say a triple bond is going to be a tight spring or a loose spring? Strongly bonded, that's a tight spring. Okay. Single bond is a loose spring by comparison. So when you look at these different resonance structures, the frequency will change because the tightness of the CO bond is changing. Over here on the left, that's a tight bond. All the way on the right is a loose bond, the CO bond. The metal carbon bond is the inverse. right? Over here on the left, the metal carbon bond is a single bond. That's a loose spring by comparison with this metal carbon bond, which is a tight spring. Okay. So infrared spectroscopy of CO is actually a really useful thing. Tells you about resonance depictions pretty nicely. So let's take a look at some carbon monoxide vibrational frequencies. So now we're talking about the vibrational frequency of CO in the FTIR spectrum, for example. You would find a band for this guy at 2143. Okay, 2143. It's really helpful to remember this number. Thankfully, it is composed of 1, 2, 3, 4. Not in that order. Okay. It's 2100 is where you're going to find triply bonded things, or carbon monoxide, nitrile, cyanide. They all appear around 2100. 1, 2, 3, 4 rearranged into 21 something or other is going to get you pretty close. 2143. Okay. All right. Now, how about this one? CO radical cation. We've oxidized carbon monoxide by 1 electron. What's that going to do to that molecule?
You're going to resonate electron.
Well, I'm going to tell you the answer because it's not intuitive. Okay. The frequency actually goes up. All right. So why does it go up? A simple explanation is that the lone pair that you're oxidizing, the HOMO, is in an antibonding orbital. That thing is slightly antibonding. Right? There are 4 sigma orbitals. That's the third one. And that is an antibonding level. The bottom 2 are sigma, the top 2 are sigma star. So you pull an electron out of an antibonding orbital. This allows the molecule to make a stronger bond. All right. So the frequency goes up. You end up with a tighter spring. Right. All right, we're going to do some excited states of carbon monoxide. There's the CO singlet, and then there's the CO triplet. Okay, the singlets and triplets for the excited states of carbon monoxide. Those guys are 1489 and 1715. Don't worry about why one is which number or the other. It's not important. But the excited state pulls electrons out of bonding orbitals, puts them into antibonding orbitals. That reduces the bond order. So you're weakening the bond. Okay, it's a more energetic system. It wants to fall apart more easily. The frequencies are therefore lower. All right, here's an important one. You can make a complex between carbon monoxide and borane. Empty orbital on boron accepts the lone pair. There's no pi back bonding going on because there's no electron pairs on boron that are very good at that back bonding kind of an interaction. So you're essentially oxidizing the carbon because the boron is a Lewis acid. Okay, what's that going to do to the bond strength? The lone pair on carbon is antibonding in nature. Okay, and we're going to pull some of that electron density off of the carbon and stabilize the CO fragment. All right, so the frequency is actually going to go up. 2165 relative to 2143. So if I said to you, hey, borane carbon monoxide complex comes in at 2165 wave numbers, what does that say about the compound? You need to remember that the vibrational frequency of free CO is made up of the numbers 1, 2, 3, 4, and it starts with 2, 1 or 2143. Okay. Okay. 1, 2, 3, 4 around 2100. It's 2143. So you got to remember that. All right. So the frequency tells you about the bonding. And next time we're going to talk about how you can read the resonance form out from the frequency. Okay. You can make it a measurement of the vibrational frequency and know something about the best resonance structure for CO ligands and for the character of the metal to which they're bonded. So we'll see you on Wednesday. Do we have class on Wednesday? There's no class on Wednesday? Wait, so we'll see you after the holiday? All right, may you have a happy Thanksgiving. I hope you like turkey or whatever it is you're gonna eat. Yeah, so the first part of your question, raising the energy or lowering the energy, has to be defined in terms of relative to what?
Relative to.
So you have, yeah, that's not a,
So if the
well,
molecule has the electron in its anti-bonding orbital, right, in the middle, and you take that electron that is in the anti-bonding orbital, and you move it.
yes.
Now you've lowered the energy of the entire molecule, but you've increased the energy of the bond.
I wouldn't use that way of talking about it, okay? I would say that by pulling an electron out of an antibonding orbital, you can strengthen the CO interaction, okay? When you say you lower the energy of everything, lowered it relative to, I don't know what.
What it was.
What energy? The
Whatever.
dissociation energy? The redox energy? See you later.
Oh, I see what you're saying. The orbital energy. So like
Compared to vacuum?
Yeah, like you did
Yeah.
Schrodinger's equation. you
Well,
had the lowest-
I would just try. The vacuum level is a statement about how electron releasing it is, right? The energy of electron in a vacuum has a certain reducing power. And you're talking about the levels moving up and down relative to it. So that's like an electron transfer energy measurement. Is this an oxidizer? Well, yeah, you just pull an electron off of it. It's going to be a better oxidizer.
Okay. Okay.
And also the interaction in this particular case strengthens. If you take another bond, like a HH bond, right, in dihydrogen, and you pull an electron out of it, the bond gets weaker. Yeah. Yeah.
Before you go,
Yeah.
I have this question.
Mary, did you have a question?
I'm just listening.
Okay.
My question, thinking about why that frequency is raised. So it is that we remove, either through removing the electrons from the antibonding molecules or through stabilizing them. It has the same effect of like force constant.
Yeah, well, because those electrons are in an antibonding level, when you pull them off of the carbon and toward the boron, or you just rip one off completely, now there's less repulsion going on. Because an antibonding orbital of this kind, you've got actually too many electrons in the sigma orbitals. So if you take two, like say phosphines, and you try and push their lone pairs together, you get a bonding and an antibonding combination, right? And the antibonding level is bad news for the bond. If you pop an electron out, now you don't pay the price of moving two electrons up, you pay the price of moving one electron up. This one actually has two going down. So in terms of redox potential, it's better. There's less electron density in that space all of a sudden. You oxidize it and you reduce that repulsion that occurs when you have all the electrons on top of each other. You stick that acidic thing to it, it pulls some of the electrons away. It makes the carbon and the oxygen feel more like positive in nature. and it pulls the molecule together. So another perspective on this thing, the frequency going up is that when you rip an electron off, everybody kind of contracts because the nucleus and the electron binding will go up. It's trying to deal with that positive charge, and it pulls its electrons more tightly, and the molecule shrinks. And that makes for a tighter bond also.
So what is the star denote? Is it fine?
CP star is per methylated cyclopentadienyl, so it's CP with 5 methyl groups on it. Like that, exactly. Yeah, Mhm.
So, just like, there's a couple like things right at the piece, so I'm gonna try to break this molecule up